Now, I've noticed a small error that some people are making with the tools we've developed to understand continual compounding. And I want to make a small point about that. And overall, I have a small point and then a point of regular size and then a larger point. But let me begin at the beginning. We're considering how we can make predictions given a set of data. We can take the list of the month of March and a bit of April with the COVID-19 cases from the United States. I've given you an assignment. I want you to try to use that data to make an argument about the efficacy, the use, the help of social distancing and stay-at-home orders. So and the first thing I want to make sure is that when we use the tool that we've developed, this continuous compounding formula, that we use it in the right way. We've invented a method, and we should use it according to the method, and not in a mistaken way. So, but to start with simple things, right there, there's the beginning of the data, the cases for the first 3 days of March. And if we just look just at the first 2 days, we could use that to make a prediction. How many cases will there be on the third day? And then we've got the actual number, so we can check the power of our prediction. And the simplest way would just be to make the assumption that the future will be like the past, and that the relevant way to look at it is as a proportional increase. We see that there are 16 extra cases from the first to the second. And we could assume that that absolute number would be duplicated, and that wouldn't actually be such a bad number given what we see. But that would be conceptually wrong. We don't expect to at the same number when we have a population that's growing, right? The number of people infected. We expect that to be determined by the number of people who are already infected. Right? The number we're going to have later is a matter of how big the population is now. How many cases have we got now? That will determine how many later, and we can expect a certain proportion increase every day. And that's why this problem gives us compounding problems, because it's a problem it's a situation that grows because it grows. But we could handle this the simple way. We could simply calculate the percent change or the percent increase from the first to the second, and assume that same percent change will be from the second to the third. If you look, if we calculate the rate, here we are, that we have today's number, 105. We're taking this from the perspective of the 2nd of March. We can compare that to yesterday's number, the 1st of March, 89. So we do this simple arithmetic, and that would be a change of 118% approximately, or we could say an increase of 18%. So if we say we have a change is 118%, and today we have 118% of what we had yesterday. That includes the 100%, because if we say today we have 100% of what we had yesterday, that's no change at all. Whereas if we say today we have 18% of what we had yesterday, that's a drastic reduction to less than a fifth of what we have. And if you say the increase is 18%, because to talk about an increase assumes you keep what you have and add some extra. So it's useful to be precise about that language. So anyway, if we take the simple arithmetic, we've got an increase of 18% from the 1st of March to the 2nd of March. And if we assume that that will happen again from the second to the third. We take our percent change, or we can calculate it again that way. That will give us the decimal version, and we multiply that by what we've got today, because we're expecting the change tomorrow to be like what the change was from yesterday. We get 124 cases, and we can compare that to the actual results. We're assuming we're trying to guess from the second, when we can actually check the true results from the third. We see we get a fine estimation. We shouldn't expect more accuracy than that. So this simple method will work. We've got the same time period. We don't have to bother with compounding. We're simply assuming that the near future will be like the near past. Now, if we use our fancier method, if we use the continual compounding formula, then we're used to its form. There it is. We can start plugging in the numbers. We know what the original was yesterday. We know what the number is today. We're trying to figure out what the rate was as a first step to predicting tomorrow. We need a rate applied to today's number to predict something for tomorrow. What have we got? Well, that was one day, and we're thinking of calculating a daily rate. So we've got the simple power of ER times 1, so that makes things easier. We can reduce that to R, and we can reduce our fraction. We can have the calculator change that to a decimal amount, and then do the simple trick that we do, take the natural log of both sides. That gives us R isolated and alone, and we can say what it's equal to. And there we get a daily rate with continual compounding. And now, this is my small and simple point. Let us note that 18 is not 16.5. Those are simply not the same number. So if we would calculate the continual compounding rate and then treat it as though it were a simple rate, that would be treating it as though it were uncompounded. And then we would introduce a source of error. This predictions of the future is not a sure business. There are many ways that it goes wrong. We have to expect our numbers to be not very accurate. But we don't want to introduce errors in our own method by misunderstanding our tools and how we made them and what they're used for. That error we can at least eliminate. This, to go back to simple methods, to make that calculation make sense. This would be a misuse of our tool, because first we calculate the rate according to continual compounding, and then we use the rate we calculated as though it were an uncompounded rate. And then we've introduced a small error, which, if you've been playing with the numbers, you see that's not very much. That the erroneous figure is still good enough and better than many properly worked guesses. As the month goes on, the time gets longer, the numbers get larger. That's still pretty good, but it does contain a misuse of our own tools. So that's my small point. Understand what you've been doing, and do not do that. Use the tools in the right way. Then the right way would be, first you can calculate the change from March 1st to March 2nd. That would easily produce a simple rate of increase, but we're interested in calculating the rate according to continuous compounding. That gives us that. And if we want to use that as a prediction for tomorrow, then we're committed to this method of continual compounding. You know, to say, since that's the rate from yesterday according to continuous compounding, if we assume that the future will be like the past, that the rate will be the same tomorrow to make a guess about what will happen tomorrow, then we again have to treat that as a continuous compounding rate. And we get something close to the number we had before. In fact, the only reason there is a difference is because I've accepted rounding and I've used slightly different numbers. If I use the simple formula with all the digits that my calculator will give me, and then again use the continual compounding formula with all the digits that my calculator would give me, then either way I would end up with the exact same prediction down to the last decimal point, because they are equivalent if you use the tools in the right way. Just don't pretend that your continual compounding rate is an uncompounded rate.